Everyone. We are at the top of the hour, so we're going to go on and kick off the webinar. I had a question that came in through the chat window that I would just want to address. By default, all attendees are muted. So if you're trying to figure out how to mute yourself, you are by default already muted. If you do have questions, you can utilize the chat feature, which is in the lower portion of your screen. You can communicate with me, the host, or with all panelists, and I'll provide a little more direction here in just a second. So thanks again for joining us today. Our webinar will be 30 minutes along with time at the end for Q&A. During the webinar, we do encourage you to send questions through the chat icon, which I mentioned earlier is just at the bottom of your screen. We are utilizing Zoom today, so hopefully we'll have a good audio connection for everyone. We will be issuing PDH certificates for those attending the live session today that have elected to receive them. You'll also receive a copy of the presentation in our post-webinar follow-up with you. All of our webinars are available on demand at bartlettwest.com, and we will continue to add webinars in the future. So we encourage you to check out our website, click on that webinars tab, and see what's coming up in the near future. Today, we're going to hear from David Stratman. David joined Bartlett & West in 2013 after spending more than 14 years in the Bridge Division of the Missouri Department of Transportation. During his time there, he's worked on a variety of projects involving new bridge structures and box culverts, as well as several bridge rehabilitation projects. David also reviewed design programs and manuals and contributed to MoDOT's design manual, known as the Engineering Policy Guidelines. Today, he will be discussing how innovative bridge design brought a community vision to life. With that, I'm going to turn it over to David. You can take it away from here.
All right, thanks, Rebecca, and thanks for everybody for showing up today to learn about the Bicentennial Bridge. Bicentennial Bridge is named so it's correlating with the state of Missouri's bicentennial of becoming a state. This is a privately funded pedestrian bridge project that will connect the Capitol complex to a landmass referred to as Adrian's Island. For many years now, the Jefferson City community has really wanted to connect to Adrian's Island, which is immediately adjacent to the Missouri River, to build like a park or trail system. And this project will hopefully, become a reality and give that to the community. During this project, there's many design complexities that went on. We'll talk about some of those today. We'll talk about some of the preliminary layouts that we looked at. And this bridge was actually designed twice, once with extensive aesthetic enhancements and one with a no frills type option. It was bid once with the aesthetic enhancements, and the costs were came in too high because this is privately funded. They had a fixed cost that they couldn't really go over, and it went over that. So we stripped off the aesthetic enhancements, redesigned it, and bid it again, and then it came much better bids. Now, since this is privately funded, the funds were kind of allocated and controlled by the Jefferson City Chamber of Commerce. And within that Chamber of Commerce, they created a kind of a bridge committee that made all the major decisions involving this. So where is this Bicentennial Bridge in the area? From this view here, Adrian's Island is about a 30-acre landmass directly next to the Missouri River. Here you can see where the Capitol complex is. That's pretty much at one end of the island. And at the other end of the island is the historic state penitentiary next to the federal courthouse. And the main issue with getting over to the island is there are 7 tracks of Union Pacific Railroad to go over. And that is the main barrier from connecting the city to Adrian's Island. Now, in the beginning, when the community was looking to kind of develop Adrian's Island, there was always issues from citizens really concerned, like why would we ever want to build over to the island when it always floods? So Bartlett & West did a hydrology study on the island, and as you can see, a lot of it does kind of flood in small events. Looking at the events here, but it takes a 100-year flood, which is a 1% chance on an annual basis that the whole island will flood. And there's many spots where it takes a significant flood to actually flood the island. So we kind of did this to kind of, ease concerns on that. When we started 5 years ago, we did some preliminary work to figure out, what a bridge would look like going over to the island. So we looked at 4 different options here, and you can see a potential trail network that kind of went around. But we'll go over these 4 options and show you what we decided on. This first option, that we call the house garage option, was very skewed. It was the most expensive option, but it had some pros. It was close to the Capitol complex. There was minimal curvature that we needed, and but some of the major problems were it had a highly skewed. Since we had the bridge over all of the tracks, and we're going in a very large skew, that made our main span over the railroad tracks over 300 foot long. So this came out to be pretty much the most expensive option, because the longer the span that we needed to go over the railroad tracks, the more cost for the girders. And I will say, all these options that we looked at were ADA accessible. That means the whole bridge was less than a 5% slope all the way down. So that kind of controlled the bridge lengths. We kept the slopes at 4.75%. Just to make sure that when they started constructing the bridge, that they'll keep it below the ADA rule of 5%. The next location we looked at was the Lafayette Street location. And again, this was on the way other side of the island. This was located next to the federal courthouse and state penitentiary. This was about the second highest estimated cost of the project. It was mainly due to extensive ADA access switchbacks that we had to create before we could even get to a bridge. This had a slight skew, so it had kind of a long span, but mainly the trail work leading up to the bridge was the most, most cost. The next location we looked at was next to Madison Street, or the governor's mansion, which is right over here. This was actually the least cost option, but this bridge kind of split the island in 2, which the committee really wanted a bridge on either side of the ends of the island, because they always imagined in the future they could get another access point to the bridge, so they could have 2 access points from in and out of the island. But this one was the cheapest option, because as you can see, it has minimal trail work right at the beginning, and it had the longest bridge actually, because if anybody's familiar with this area, this is way high up on a rock bluff. So, and if you looked at the hydrology map that we showed earlier, this is on maybe the lowest part of the island. So we had the highest point at the start of the bridge and the lowest point on the island. So that made for the longest bridge. Now the chosen option that we had is what we call the Senate garage option. This is a circular structure right here. The pros of this one is it's immediately by the Capitol, so it was promoting, likely this is the location that would promote the most foot traffic on the bridge. The estimated costs were just slightly more than Madison Street, but the bridge also ended basically on the highest point of the island, ensuring the bridge would really never get flooded. Some of the problems with this location, which we'll talk about a little more, there's a slight pinch because on this other side of the Senate garage, there's the Veterans Memorial, and this is basically a retaining wall right here. So in between the retaining wall and the Senate garage, there's a bit of a pinch that's less than 10 feet, maybe 9 feet wide, right in just a narrow portion of there. Some other issues with this is we have a fairly long span here. adjacent to a very short span here. And we've tried to make this short span as long as possible. And we'll get to some of the issues with that a little later on. And there's also a historic retaining wall that we had to avoid that runs right around here. This is a little snippet from our bridge plans. And I just wanted to show this because differs from this preliminary option that we looked at like 5 years ago, and from the final plans, it changed a lot. This abutment was very complicated to locate, I will say that. As you can see from, we did some geotechnical explorations before we finalized the bridge plans, but you see there's two very closely spaced ones here. That's because this first one here actually hit the foundation of the Senate garage. So they moved over a couple of feet and they drilled another hole and they got down to rock eventually. As you can see, we have a wing on this side that is basically getting butted up against the Veterans Memorial retaining wall over here. And then this side of the abutment is butting up against the Senate garage right here. And then we ended up sliding the bridge over because of this one boring. They found the foundation of since they hit the foundation of the Senate garage. So we had to slide the bridge over a little bit. And then we skewed it more at this end just to get right in between the foundations of the Veterans Memorial wall and the Senate garage wall. Try to avoid any of our piling or whatever we're going to use for support this abutment. Try to get as far away from that as we could. Now here is a look from that abutment, looking out, towards where the bridge will be going, out towards the island, this landmass over here. Here's the historic wall that we had to avoid for pier. Here's an existing, landscaping small block wall here, and our abutment's going pretty much behind here. Another thing we had to avoid, as you can see, next to the Senate garage, they have these windows, what I'll call, on the garage. So our abutment had to not be up here blocking one of these windows. We had to space them in between these windows and make sure we weren't, making our abutment up here, so we'd have to block off this Senate window with fill or whatever. Here you can see the actual boring locations where they drilled. Right, this is the first one, and then another one they moved over here. So fitting this abutment in had many machinations. We had to adjust it a lot during the final design process. Okay, so like I said before, we did this initial design with very aesthetics. The bridge committee wanted to see, how nice we could make this bridge. So they looked at various options of overlooks, kind of expanded the bridge deck out, some decorative acorn lighting. They wanted to put maybe a very decorative access gate at the beginning of the bridge, and they wanted a gate there anyway, just because in case the island did flood, they didn't want people, walking. They wanted to close access to the bridge so people wouldn't go down to the flood. They kind of, want to keep Michael Scotts from using their GPS and running right into the water. It's for the Office fans out there. The most most costs arise from what we call this rail car design that they came up with the aesthetic options. Now this idea came about mainly due to the railroad's demands on what they needed for our span over the railroad tracks. They, in most applications, bridges over railroad tracks, they kind of want a taller fence, like maybe 10 feet tall, maybe it has a curved top on it. But in this case, since they knew this was probably going to be a big tourist location, have a lot of pedestrians on it, and they're going over 7 lines of their rail, they wanted a top over any fencing that was going to go over the span over the railroad tracks. So knowing that requirement from the railroad, the bridge committee kind of hired an architect and came up with various ideas of how, well, if we have to have a top on it, let's make it as decorative as possible. So they came up with this idea with showing like a pedestrian train, or uh, uh, train cars that kind of covered the railroad track on a main span. The inset pictured over here is the actual no frills design. It's just a framework of chain link fencing. And that's what eventually went to. But having the rail cars on this bridge structure caused many kind of design issues that we had to deal with. The majority of them was, since it was basically a building structure on a bridge, if anybody knows what, ever been on a bridge, on a highway bridge, while they're stopped and while other vehicles are driving along, you know that bridges really bounce and deflect, and you don't really want a building to bounce and deflect a whole lot. So that was the main issue with putting the rail cars on the bridge. So me being the engineer saying, whoa, how am I going to control these, and the main thing I was worried about was what I call differential deflection. That means the difference in the deflection at one side of these building structures to the other side. The one next to what a pier location wouldn't deflect hardly at all because it's right next to the support, but the one out closer to the middle would deflect a lot. So we looked at stipulations in the building codes to see what kind of differential deflection was allowed on building structures, and we came up with about a 3/8 of an inch control deflection for the building structures that we wanted to have the difference in deflection from one side to the other. So seeing, knowing that structures don't really get put on bridges a whole lot, I decided to do a little Google search to see what I could find. And this is about the closest thing I came up with to having a structure on a bridge, which this is basically a strip mall in Bulgaria, where there's shops on either side of the bridge and the pathway down the middle. But this was a concrete deck girder kind of bridge, which doesn't deflect much, and the span is about 90 feet, or over half as much as what we need to go over the railroad tracks. Other things I seen were like concrete arches that were very short. You had building structures on that, and on lock and dam type structures where they have like a maintenance shed, but it's always located right over a pier location where you're not worried about deflection. So knowing this, we came up with, try to look at 3 different structure items. Originally, when we did all the preliminary work, we just assumed plate girders, structures to go over the railroad tracks, just because at that time, we're just looking at, low cost options for everything. But knowing that we wanted to go with possible rail car structures on it, we tried to maybe look at different options that might work for us. We looked at a through girder, truss, and just the regular plate girder options. So what's a through girder? A through girder is basically 2 big girders on the outside with a deck kind of supporting them in between. Now to get our deflections to work, we would need a through girder that was over 10 feet tall. The contractor we were working with, and we talked with the fabricator here, local fabricator here in town, they were a little worried about dealing with girders that big. So we kind of nixed that idea. The other idea is kind of a truss, which you'll see kind of like, overpasses on walkways over railroads. Like this is our highways. This one is at St. Louis Science Center, where you can see the truss members are inside here. And this is probably a viable option, but time was not really on our side to design a whole big truss. So we kind of went with the more simplified structure of a plate girder. So how do we solve that deflection issue? With the rail car option, what we had to do was add a third girder, which on a pedestrian bridge that's not very wide, a third girder can add a dramatic amount of cost, but it's kind of what we needed here. And also in traditional design, when you're kind of calculate deflection, you just kind of use the, what I call a tributary width of the concrete slab that the girder is supporting, along with the girder section, to calculate that deflection. But since we couldn't get that to work and limit our deflections that we had to get to, what we did was we added a concrete curb into our stiffness calculations. Now, the curb we had to have because of another railroad stipulation of they didn't want any water, draining off the side of the bridge onto their railroad tracks. So we had to have a curb, but in this case, we made it structurally instead of just being a gutter. We had these, I think they were about 2 feet tall curbs that we included in our stiffness calculations to reduce deflections. Now, not only did we have to do this for the railroad structure, but for our stripped down version, we also had to use curbs for stiffness to reduce our deflections. This is a cross-sectional view of the slab that is going to be built. This is about a 2 foot tall concrete curb. The girders themselves are 66-inch webs, but what it did was, since we had about a 200-foot span, our what we call a live load deflection from all the people loaded on here, the limit that we're trying to shoot for was 2.5 inches. And without using the curbs as the added stiffness to reduce deflection, we got about 3.5 inches of deflection. So when we added the curbs into our calculations, we reduced the deflections to about 3/4 of an inch, or about an 80% reduction in the deflections. Another design consideration, since this is a pedestrian bridge, all the piers were single column piers because it's not a very wide bridge, so it doesn't really make sense to have multiple columns in here. So one of our big design considerations was actual lateral wind loading. As you can see, these rail car structures were approximately 15 feet tall and 40 feet long, and times 4 of them on there in the middle span. Basically, and also, since they're corrugated steel, the wind wasn't gently blowing over all of them. It's basically a big wind sail catching all the wind that they can. Increasing that wind drag coefficient, we got basically a 200,000 pound wind load that we had to put on our bridge. So how do we handle this? Nothing too fancy. We just had huge columns on either side of the railroad tracks. This is an actual cross-sectional view of our rock sockets. All the piers were supported on drill shafts to rock sockets and socketed into rock. We had a 5.5 foot, this is the final, the no frills type option with the 5.5 foot diameter. And if you see the reinforcement at our Pier 3, we had to have number 18 bars in bundles, which, if nobody's familiar with what a number 18 bar is, it is 2¼ inches in diameter. So we had very heavily reinforced large columns to handle that lateral wind load. The option with the rail car options, with the rail cars, with the aesthetics of that, we actually had a foot difference. We had 6.5 foot columns in rock sockets. Some more design considerations we had on this bridge were uplift. I kind of coincide uplift with a teeter-totter, where you have one big weight kind of pushing down on one side and uplifting the other side. And for this bridge, there's kind of 2 methods for this uplift that we had. One was due to the curvature, and one was due to having that really large span over the railroad tracks next to the very short span next to the Capitol. So this picture here is part of our plans. It's basically the center line of our structure is represented by this line here. And this is the curvature we had to have in our bridge to get back down to the island. If we zoom into this, how do we get uplift with the curvature? Well, if you think of this line here represents one pier, whereas this line here represents another pier. So if we draw a straight line or a chord to those locations, that's kind of like the center line of the, the center of the teeter-totter. And anything, since the center line of the whole bridge, there's an offset there, that means there's more weight on this side than there's going to be on this side. So since we have two girder lines, one on this side of the center line and one on this side, there's more weight put on the outside than there is on the inside. So to limit those uplift forces, we basically just kind of kept our span lengths short enough to not amplify that uplift effect to like 90 feet. And that worked out well with we used wide flange beam sections for this curved section. So that helped reduce costs. The other issue of uplift was basically, like I said before, this very big span that we had to go over railroad tracks next to our very short span here. And this is why I wanted to make this span out here as long as possible so I got those as close as I could to the Senate garage and the Veterans Memorial Wall. Basically, in this case, this is like the center of your teeter-totter. So all this weight over here is kind of pushing down and lifting up on this side. So in our final setup, we didn't have a whole lot of dead load uplift. It's basically next to nothing. It was just very little downward force, actually, just for the dead load. But any uplift forces came from our extreme design case where this whole big span was loaded with people. So it's mainly a live load uplift issue. So how do we deal with that? We definitely made sure we poured that abutment integral, which means we basically surrounded, the girders in concrete and tied it into the beam that they're sitting on. The other thing we did was we utilized a micropile, which we embedded into the rock foundation below. Now, so they're kind of like mini versions of the drilled shafts and rock sockets that we use at our piers. As a secondary, solution for using micropile, one, we had that tight access. We had the pinch point next to the garage and Veterans Memorial Wall. So with micropiles, there's a smaller equipment that they could, easily drive through that area. Also, since, it's right next to the Capitol complex and there's numerous, stone masonry type stuff going around there, we wanted to disturb, limit the vibrations, any construction vibrations, and limit any, effects that we might have by, driving piles. So micropiles, what they utilize they're drilled instead of hammered in. So that would definitely minimize that to, be mindful of all the historic structures around the Missouri State Capitol. So here what we have is our final layout. We have two units basically, one that was mostly straight, but the plate girder option. 77 feet, 208 feet, 111 feet. And like I said, it was a 66-inch deep web. And here we have our covered chain link pedestrian fence. And then the second unit, kind of separated with a expansion device at this pier here, was wide flange beams, to simplify the design and the costs. Here you can see where our flood elevations are, and this is the 500-year flood. And it, run that over here, and it barely gets up to the right at the girder elevation. So you can see the bridge will probably never flood, but other areas on the island will, but the areas around the bridge won't ever flood. So here we have a video. Since I said this is a privately funded project, this is kind of a marketing video that we created as a fly through. through the area. On the right, you see the Senate garage. On the left was the Veterans Memorial Wall. Here, one of the aesthetics that may still come about is these steel perforated panels that might show historic Missourians. That's not really finalized yet, I don't think. And this is just part of areas that might get, remove the chain link fencing and put these in if they have, money left over in the project. So this is just a view going down to the island, showing the end of the bridge. There's an extended version of this video showing kind of more of the island park stuff that might go on there, and it kind of goes back and shows what the bridge might look at night. That is located at bicentennialbridge.org. It's a website that was created to help raise funds, and if you want to see an extended video, you can go there. And that is all I have as far as my presentation. So Rebecca, is there any comments or?
Yes. All right. Thank you, David. At this point, we're going to open it up for Q&A. Please send your questions through the chat icon, which you can find at the lower portion of your screen. We'll wait a couple minutes for questions to come in. And while we're doing that, I do have a couple of questions here. I believe one was answered, but David, I will let you see if there's any additional insight that you want to share. The question came from Scott, wanted to know the Madison Street option. Is that the location of the original Missouri River Bridge? Bob answered the original Missouri River Bridge was at Bolivar Street, several blocks to the west of the Bicentennial Bridge. So I don't know if you have anything else to add. I'm not familiar with the area, so I thought I would still put that out there.
No. One thing I forgot to mention, removing those aesthetic enhancements of the rail car structures basically dropped $1 million out of the cost of the bridges. So that was the difference from, yeah.
All right, we also have another question here. Is it a true island surrounded by the river or just a low area next to the river and it is just called an island?
Yeah, I don't know how exactly called an island. It's more like a peninsula. It's kind of separated by Wares Creek that kind of runs along the edge along the railroad tracks, but it's mostly a peninsula area. It just has the name of Adrian's Island.
Thank you. Another question from Sharon here. Any considerations for harmonics during celebrations like fireworks, festivals, people swaying to music?
We looked at that briefly, but we think adding the curb to the structure really stiffens it up, and I don't think there would be any issues with that. Maybe some on the wide flange section, but those spans are fairly short and not, the major 200-foot spans that we had to deal with over the railroad track.
Great, thanks, David. Another question here, is this definitely under construction now?
Yes, it got bid a couple months ago. They currently are not working on it, but they do have notice to proceed, and I think the contractor said they're going to try and start on it this fall.
Great. Another question here, curious who's picking up the maintenance for this project?
Yeah, after this bridge is built, it'll be turned over to the city, and it'll be, incorporated into their parks division, and the city will be taking over the maintenance.
Perfect. As we wait just another couple minutes for questions to come in, I do want to thank everyone for sharing your time with us today. David, thank you for sharing your expertise with us on this very cool project. As a reminder, a recording will be available on our website at bartlettwest.com. David's contact information is provided here on the last slide, and you are welcome to contact him directly. I am not showing any further questions at this time, so I want to thank everyone again. Have a great rest of your day, and we look forward to seeing you again soon. Everyone, thanks so much for joining. Have a great rest of your day.
Thank you.